Yes, of course I can switch to English. I apologize. No, it's perfectly fine. I even made the slides in English, so sorry, that was nothing but habit. I'm not going to start all over though, except at saying welcome. Yeah. Okay, good. Very good. So what we're going to do in this talk, you will see that there's a little deviation from the program. It said that this should be about math juggling and Python. I think even something about hidden Markov models. And the reason that I changed the talk a little bit is that the project I'm going to present has changed a little bit over the half year since I started. So that's why these are going to be the topics for today. So what is a smart juggling ball? Why do we need a smart juggling ball? I like to juggle. I think it's great fun. And I would like to have a juggling ball that, first of all, knows when it's being juggled and how it's being juggled. I would like to use some kind of embedded electronics, maybe some software to kind of tell me when I start juggling and what kind of juggling I'm doing. So this is definitely something we are going to look into. I don't know why that one switches off. So that's what we're going to talk about. What are we going to need to make a smart juggling ball? Well, definitely we're going to need some math. And I'm going to spend quite some time today talking about math. And why do we need math? Well, let's look at a few juggling patterns together, just to kind of get us all going. Ja. Er det ikke så veldig god lyd? Ok. Ok. Er det alle hører dobbelt? Oh. Okay, stop making the... Okay, is that better if I talk like this? Okay, cool. I will take off this thingy and get rid of the wires, and there we are. Okay, thanks for letting me know. So I hope that you can still hear me on the back row. Let's look into a few juggling patterns. And I think that if some of you have tried to juggle two juggling balls, you have probably done something like this. Or if you are left-handed, maybe you juggle the other way. But still, you juggle with two balls, something like this. Or if you are really courageous, you change the direction as you are juggling. So one ball goes high and the other one goes low. And already we are starting to talk about juggling and patterns and throwing with a natural kind of language. So I say that, you know, there's a high ball and there's a low ball, which goes much, much faster. So we can see that when I throw a high ball, the low ball goes really, really fast to the other hand. And it has much more time because one goes high, takes time, the low ball goes really, really fast. So I have time to do things with the low ball. And then I can start to do things like this. I can add a little throw back to the same hand to make this go continuously. And a small throw back to the same hand, a throw to the other hand, a high ball. This is a way for me to talk to you guys because you understand English and you understand this. But to make computers understand this, we need to do something a little bit more precise. We need to describe juggling in a different way than using things like low to the same hand or to the other hand and so on. So we need to kind of put juggling on a solid mathematical fundament to make it able so that computers can start to calculate things on this for us. Because that's what we want to do in the long run. And I'm starting to get warm, so I can get rid of my beautiful scarf. That's good. Exactly. So when we start to make mathematics, we're going to need some kind of starting point, some kind of assumptions about juggling. And I'm going to do this now. I'm going to make my assumption completely explicit. And then we're going to apply some logic. And out of this assumption and the logic, we're going to develop a complete, entire mathematical system of juggling. Is everybody familiar with the term logic? Do you know what logic is? Anyone? There's a guy a little bit courageous in the corner say he knows what logic is. So let's test him. Here I have a little candy. It's black, and I put it into one of my hands. And I'm now going to make two statements. And your job is to tell me where the candy is. So first, the candy is in one of my hands. It's in either of these hands. There is a candy. And then the second statement, the candy is not in this hand. Can now somebody please apply some logic and tell me where this candy is? Anyone? Volunteers? Hey, well, no, I'm not lying. The statements are true. So definitely they are true. So obviously it's going to be in my right hand, right? So you can take this one and eat it. But that was very easy. Can we try to do one more, a little bit more complicated? I have a black candy and a white candy and a black candy. I'm going to need a volunteer. Edle, can you just come up here and stand with me for a second? And if you just come here, I want to hide them and nobody must see where they are, okay? Okay. So, okay, close your eye, guys. Okay, come here. And you put this one there, and you close your hand. And then, oh, okay, that's fine, okay. This one and this one there, okay? Close, good. Then you come next to me. That's right, and now I'm going to make a few more statements. There's a white candy and there's a black candy. And the white candy is never next to an empty hand. Are you with me? The white candy is never next to a white hand. And the two candies are always in adjacent hands, so there's no empty hand in between them. And then the third statement is that this hand is empty. Can somebody please tell me where is the black candy? Oh, there's a fast guy on the left side.
On the right.
On her right hand.
No, the left.
Her left? Okay, so can you come and point? You want me to repeat? That's always safe. Can you please repeat the question? Always safe. But okay, so this hand is empty. The two candies are always in adjacent hands that are next to each other. And the white candy is never next to an empty hand. No, can you please tell me where the black one is?
The right hand.
In her right hand. Yeah, can you open and look? Oh, God, you got it right. Perfect. So then we can give him the black candy, and you will have the white candy for coming up. Thank you. Great, so this is logic. Now we know that. Okay, so we're going to start to have some statements about juggling, and then we're going to apply logic and make a mathematical system. That's good, let's do this. So these statements are sometimes in mathematics referred to as axioms. And an axiom is a statement about the world which is always true, can never be false. So that's why it's a good starting point for using logic. So our first kind of thing that we're going to decide about juggling is that we're going to throw with alternating hands. Left hand, right hand, left hand, right hand. Now we could imagine that I would juggle in a way in which I throw with both hands at the same time. But today we're only going to talk about juggling, which is alternating left and right. So this is our first true statement about juggling. And the next one, we only throw one ball at a time. In some types of juggling, you can do things like this. You have two balls in one hand, and if you are good, you can throw them up with different height. This is called multiplexing. Today, no multiplexing, only throwing one ball at a hand, from one hand and one ball at a time. That is the second kind of starting point, or kind of guaranteed truth about juggling. And the third statement is an even rhythm. I'm going to have an even rhythm. So I'm going to try to keep, when I'm juggling, try to have an even beat as possible. So there's a kind of rhythm in everything I'm doing. And they're going to be equally spaced in time. And if we have these three statements all together, we can start to apply our logic and create what I think is a really, really beautiful model of juggling. Any questions so far? Everyone is happy? Yeah. Okay, that's good. Everyone is happy. Awesome. Great. So when we have this kind of statement, alternating hands and even rhythm, we can lay out our hands in time. So I will say, imagine that this is the right hand, left hand, right hand, left hand, and time is going from this side towards the right side. And then we have our beat kind of established in this little drawing. And then we can start to look at different ways of throwing. So here's one way of juggling a one ball pattern. And it basically goes from my right hand to my left and back, an even rhythm. And what I'm doing here now is the same thing you see drawn in the symbols on the screen. So this throw is being thrown, and then on the first subsequent beat it's being thrown again. So it's just 1, 1, 1. Are you guys with me so far? Yeah, that's good. Obviously, we can start to throw a ball in such a way that it's being thrown on the second subsequent beat. So I throw something from my right hand, and then I throw something from my left hand, and then I throw the same ball again from the right hand. So this is what you're seeing on the screen behind me right now. Same rhythm, same speed, same time between my throws as when I was operating only with one ball, except that now I have two. And of course, so we can go on and go on, you know. Every time I throw a ball like this, I need 3 balls, and each balls are going to be thrown on each third subsequent throw. And then it starts to look something like this. And then you are maybe curious, is it really true that the balls are being thrown on each third throw? So I can replace these guys with some balls in other colors. And I think I have an orange one, and I have an orange one, and I have a yellow one. And I can start to do this like this. And if you now start to count, we can count on the yellow. So let's say 1, 2, 3, 1, 2, 3, 1, 2, 3. So they are being thrown each third beat. And of course, we can do the same thing with 4 balls and 5 balls and 6 balls and so on. I'm going to do some 4, maybe some 5 throws later, but I'm going to stop with 3 balls at the same time. And you can start to make some observations already. And that is that when I throw a ball that is going to be thrown again after 1 or 3 or 5 beats, it is crossing hands. It goes from left to right or from right to left. And that makes sense because there are 2 hands. So if it's going to be thrown on every single throw, it needs to change hands for this to add up. And similar, if it's a 2th row or a 4th row, which is a bit higher, it has to go back to the same hand for this to add up. We had 3 axioms, and one of the things we said that it should never be more than 1 ball in a hand at the same time, and therefore some combination of throws becomes illegal. It is not legal to throw juggling balls in numbers with falling numbers, because if I throw a 2 throw from my right hand, which goes back to the same right hand where it comes from, and then while it's in air, I try to throw a 1 throw, which also goes to the right hand, and I do this at the same time, these balls try to land in the same hand at the same time, and I really struggle to catch them, so I can't do that. And of course, the same thing is true for throwing a 3 and a 2 or a 5 and a 4, for instance. They will end up in the same hand at the same time. Can't do it. It's illegal. And it kind of follows logically from our axioms. What I think is truly fascinating then that we can now start to combine throws of different height. And I've shown you this one already. Here we have throws with different height. And we start off throwing a 2, followed by a 3, followed by a 1. And then we can repeat this all the time. And it looks like, so it should be a 2, 2, 3, and a 1. Let's see, that's 2, that's a 3. Ah, yeah, here we are. This is the pattern that I showed you initially. And this is the pattern that you see drawn on the screen behind me. And of course, these juggling patterns, they get names from the numbers of throw that we do, or the sequence in which we throw the balls. So what I just showed you is a juggling pattern which we call 2, 3, 1. That is the name of that pattern. Yeah? So far, so good. I don't know why this thing is switching off every now and then. I don't hope it's my computer which is failing. Yeah. Okay, so far I think we are doing what is quite easy. Now I'm going to come to probably the most difficult part of the lecture. So try to stay as much awake as possible, and I will try to be as slow as possible and see if you can understand this. Because what I want to do now is to try to take these kind of things we just saw and generalize them into a much more general pattern about juggling. So imagine still that we have our time. Right now, in this very moment, this is this line right here. So I have been throwing some balls in the past with 3, so they are being thrown again 3 beats later. And because this is right now, and we know how they are thrown in the past, we can say that on the first subsequent beat, there's a ball ready to be thrown again. On the second beat, it's a ball ready to be thrown again. And on the third beat, there's a ball ready to be thrown again. So this is just the same thing that you have seen when I juggle 3 balls. And now imagine that we move time forward, and I throw this ball. So this ball will then be in the past, and then we throw this one, so it lands here. So that's also another 3. And that's going to look like this. So this one was in the future. Now it's in the past. It has been thrown. And we have once again ended up with 1, 1, 1 standing underneath this timeline. So because of this, we can draw this in a different manner. We can draw this like this. Just 1, 1, 1 inside a little circle, and an arrow with the number 3 pointing back to the same circle. So what I'm trying to do here is to build a kind of state diagram of all possible juggling patterns that we can do with 3 balls. Are you guys with me so far? Let's do a few more examples just to make sure. So imagine now that I decide to throw this ball here, because this one is the next beat in our timeline, which goes like this. And if we throw this one into a 3, we would get back to this point. We would once again have 1, 1, 1, and we will have the same pattern. So let us instead assume that we don't throw the ball as a 3-beat throw, but as a 4-beat throw, like this. Because I throw it a bit higher up in the air, there is at the moment not schedule any ball to land on the 3rd subsequent beat, but on the 4th subsequent beat. So obviously I have to add a new state into my state diagram. And can any of you guys try to imagine what that state is going to look like? Anyone who wants to try to come with a suggestion? So there's going to be an arrow out of this one that says 4, and it's going to come a new state, and what's going to be inside that state? 1, 1, 0, 1. That's absolutely perfect. Absolutely correct, I mean to say. That's right. Exactly. And imagine now that this one is the next to be thrown, because still our time is moving in this direction. And now I want to throw this one in such a way that I get back to this state right here. Does anyone want to try to make a guess at what kind of throw that needs to be? 2. That's way too fast because nobody else can think, but it's correct. So it's going to be a 2. Yeah, as you can see, the 2 goes in and fills the gap, and that's going to bring us an arrow back to the state that we were previously in. So now we have 2 states. Are you kind of understanding how this pattern is being built up? Let's try to do one more just to make sure. So imagine now that I decide to throw a 5. And obviously we are in this state at the moment because we threw from here 1, 1, 1. So we are in this state. There's going to be an arrow out with a 5. And this time you guys can't reply because I know that you know it. So anyone else who want to tell me what's going to be inside that next state? 1, 1, 0, 0, 1. Okay. Very, very good. So we all got this sort of. It's kind of easy to understand. And then we don't have to do all the mechanical work of filling out these states. So I can just show you the complete state diagram. And it looks like this. It's beautiful, isn't it? This is a complete abstract modeling of three-ball juggling. I think it's beautiful. And you can also see that there's a few things in here which we haven't talked about. For instance, we are able to get into this state. And then there's a 0, and we can get back to having a 0 throw. And what that really means is an empty hand, a hand where there's nothing going on. And I'm going to show you a few examples in a second. I just want to summarize a little bit because I think we did something really important here. So we started off by identifying our axioms, our 3 kind of fundamental statements about juggling. And they are here. And they are really explicit because they are about hands. We say, alternating hands. They are about balls, and they are about time, about rhythm. So here, everything is very, very explicit. But as we kind of progress, we went over to this kind of analytical little tool, little drawing that helps us. And still, we have time along the timeline, and we have something about left and right hands, høyre og venstre, for those of you who don't read these characters, and the number 3. And then, when we start to generalize this into a more general pattern, suddenly hands disappear. There's no more reference to any hands here. There's no left, there's no right, there's nothing. And eventually, when we get over to this point, there is no reference to hands anymore. There's no reference to time anymore. It's just a kind of static diagram that holds a lot of state, kind of devoid of all reference to what's actually going on. And this is the concept of mathematical abstraction. So we start off with something extremely specific and concrete in the real world, and we end up with a very general model, which is abstract about juggling. And of course, once we have this model, we can start to do really, really cool things. For instance, we can start to go on a tiny little journey. Because you have seen the juggling pattern 3 already. I've done that a few times for you guys. It looks like this. And if we start to look carefully into that diagram, we see that it's possible to do a 4 that brings us up to this state, and then we can do another 4 which brings us down to this state, and then we can do a 1 and we can return back to the original state. So it's possible to juggle the pattern 4, 4, 1. That is a continuous juggling pattern. And I'm going to show it to you in a second. But 4, 4, 1 is a kind of important pattern because when people started to analyze juggling back, the first person to do this was a guy called Claude Shannon. Maybe some of you have heard of that guy, the father of modern information theory, was the first person to have a real go at making a mathematics of juggling. And then throughout the 80s in America and in England, groups independently developed this kind of system, which is called Siteswap. And what's interesting is that the pattern 441 is not known to have been juggled until it was proven mathematically that it was possible to juggle it. And I think that's really, really true, that we start off with some assumptions, and then you can prove that certain juggling patterns are possible to juggle, and then of course somebody starts to practice and actually learn to juggle it for the first time in history, made possible by analysis. So we remember that we had 3 throw, which is like this, and a 4 throw is a throw which takes 4 beats before it's thrown again, so it's quite high back to the same hand. And then it says that it should be possible to throw a 4, a 4, and a 1, and it looks something like this. This really deserves applause, people. And of course, there's a myriad of beautiful patterns inside here that you could discover. But there are some challenges, because initially we started talking about that we want to make smart juggling balls because we want to kind of visualize what's going on. So why do we need to visualize? So let's take a gentle look at a few different 3-ball patterns. So you've already seen the 3, which is this one. And then there's a pattern which consists of a 3, a 3, a 4, and a 2, and then repeats. And 3, 3, 4, 2 looks like something like this. So here is 3, 3, 3, and here is 3, 3, 4, 2. And unless you are an experienced juggler, it's not very easy to tell these juggling patterns apart. They kind of look a little bit like the same. So once again, what we can do to make these patterns more clear, what's kind of more visually strong, what's going on, I can exchange the ball with one of the balls in another color. So I have 2 orange and 1 yellow, and then I can do like this. And now I think it becomes quite clear that the yellow balls stays in my right hand all the time, where the 2 orange balls crosses between my hands. Can you see it? Yep. Yeah. That's nice. Now I can use a ball in a different color to kind of make it more visible what's going on, make it a bit more clear. But the problem is, of course, that in the moment I add another 3 in here, it doesn't add up any longer, because it will look like this. So here comes the 4, and there's a 4, and here's a 4, and this one, this ball, I really would like this one to be yellow, so that I would like to have a smart set of juggling balls that can change colors accordingly by themselves, so that I can see what's going on. That is kind of the whole idea, the whole motivation for trying to build a small juggling ball. You guys are laughing, but just wait, give me 10 minutes, I'm going to put this into a larger historical concept, and you will see that, wow, it's super useful, even though right now it seems more like a toy project. So a smart juggling ball, we need some kind of electronics and some kind of stuff. And here comes the embarrassing part. I've been working on this project on and off for the last 8 years. And I still haven't succeeded in making a smart juggling ball. So, you know, maybe I should find myself a completely different job. But anyway, I started doing this project together with Roger Antonsen from University of Oslo. He's a mathematician and a juggler. And he even got a little grant from the Norwegian Research Council to try to make this smart juggling ball. And he worked really hard on it for a while, and then, you know, time takes over other things. And we kind of got halfway there, but we never managed to drive it all the way home. But I give talks like this quite often, and a couple of years ago I gave a talk at the Oslo University College, and I met these 4 guys. And they were in their first year of their bachelor thesis, and they were so fascinated by this whole math and juggling thing. So when they were in their 3rd year, ready to do their bachelor thesis as engineers, they came to me and they said, hey, can we try to build smart juggling balls? I said, great, I'll take you on and I'll be your supervisor. That's awesome. So this is Johan, Johannes, Jakob, or Håkon. So did this project. So then we started to kind of look into this. So what do we need to make a smart juggling ball? Well, we are obviously going to need some kind of electronics. And this is the circuit board that these students designed for this project. And it has all the things that you would expect to find in a kind of embedded system. It has a microcontroller, tiny little device that can do computations and talk to different sensors and so on. This is an STM processor, 96 megahertz, lots of RAM and all the things you need. In addition, these balls may have to exchange some kind of information about when they are being thrown and when they are being caught and so on. So we have a radio in there, which is great. We also need a sensor, which is the little tiny device here, which is an accelerometer that measures acceleration, and it's also a gyro that measures rotation. And the gyro is very useful because we want to do free fall detection. We want to know when the ball is in the air versus resting in your hand. And to fit in the battery, we made a big hole in the middle, which means that the accelerometer is no longer in the center of gravity of the ball. So when the ball is rotating, if you throw it a bit onward, it won't be able to calculate that it's free falling. So we need a kind of gyro to compensate for that. And then finally, we want to see colors in or light in different colors. So we have 8 3-colored LEDs on the circuit board, 4 on this side, and then 4 on the back side, so that the ball can have a kind of beautiful light. We're definitely going to need a battery to power the whole thing. So there's a rechargeable solution for this, lithium-ion battery, with a little bit of energy, sufficient to power the ball for an hour or maybe 2 hours. And then the most difficult thing of all is this. And this is much more important than you can possibly imagine. This is the shell which will kind of encapsulate all the electronics and make it into an actual ball. And to make a good shell turns out to be much, much more difficult than you guys can possibly imagine. Because I am a juggler, and when I have a juggling ball which is kind of soft and so on, I'm quite relaxed when I'm juggling. I feel that I can stand here, I can juggle 3 balls, I can talk to you guys. And if 2 of these guys kind of crash in the air, I don't care so much because they just fall to the ground and I can pick them up again and continue. In the moment you take a juggling ball like this and it has some kind of really hard 3D printed horrible plastic, I am so terrified when I'm juggling 3 of these balls that I'm happy there's a carpet here, because it's a wooden floor. I would be so stiff and kind of unrelaxed when I juggle them. Because when 2 of these guys hit each other mid-air because I don't do my juggling properly, it's like my heart stops because, oh my God, thousands of hours of work is going to crash into the floor in a second, you know, it's horrible. So I think, you know, as kind of engineer, it's so important to think about the human aspect of the products that we make, because this is actually a complete useless juggling ball because of the material from which it's made. So that's an important lesson to take with us. What is the last thing we need in our juggling balls? Any ideas? Software, yes, you're going to need some software. That's exactly right. Very good. And in this project, we were kind of standing in the choice between these 2 guys. Shall we use some kind of C Arduino-based thingy? I have made quite a lot of few projects in Arduino. I like Arduino, and I feel kind of familiar with it. And then the question is MicroPython. When we had this discussion with the students, maybe, you know, February this year, I said, oh, Python would be so exciting. I would like to learn more Python and so on. So after a bit of thinking about it, we landed on Python. I'm going to spend a few minutes now talking about why that was a bad idea. Yeah, I really regret it, actually. So the good thing about Arduino is that you compile before upload, then you kind of do your stuff, and you're happy. MicroPython, these little chips that you can have inside the microcontrollers. When you connect this with USB to the computer, it pops up as a device, as a kind of hard drive or USB stick in your computer. And you can edit the Python straight onto the device, which you think is a very good idea. But if you guys are going to try to do something like this, you have to get yourself an editor with really, really good syntax checking. Because if you don't do this and you upload a code which doesn't work perfectly because there's a wrong indentation or you have a runtime error, you get no feedback. The program just stops working on this little embedded device. There's no big dump of error message onto your screen saying in which line is the error and so on. So I think that, you know, this argument that you can edit on device is not really a good argument. It's actually just a hassle because I end up making just the slightest programming error and the whole thing crashes. Of course, it's possible to do some kind of compilation of Python onto this MicroPython bytecode, which executes a little bit faster, and you also get a little test of your syntax and so on before you deploy, which is good. But then, of course, you lose this ability to edit on device. But you don't want that anyway, so that's fine. At least that's my opinion. Maybe some of you guys disagree. Faster to execute. C, absolutely true. Much, much faster to execute. Even on a much simpler and cheaper device, the C code executes much faster. Faster to prototype is an argument that we have heard several times today on some of the Python talks, that, oh, you can just open editor and you can do all this magic stuff. I think that this may be true when you write algorithms. But in an embedded system where you have microcontrollers and you have devices that you want your microcontroller to communicate with, this is not really true. Because I mentioned to you that one of the most important sensors that we have inside our juggling ball is the accelerometer. And the accelerometer and the slash gyro and also a 3-degree compass magnetometer, they are complex devices and they have lots of registers and a lot of settings about sample frequency and filtering and interpolation and what God knows. And to set up this device, you really need to know your device well, to write to the registers and so on. And is that code going to be faster to prototype in Python? I don't think so. I think the time-consuming part here is really to know your devices and to interface them more than actually writing the code. I know it's late in the evening or in the afternoon, but this is some of the Python code that you need to set up this accelerometer inside the juggling ball. And it's a lot of stuff that you need to know about addresses and how the device is kind of constructed to be able to configure it. The corresponding code for Arduino looks like something like this. Of course, we don't have to understand all this code, but I don't think that this is any more complex or harder to write than the Python code. So I don't personally think that the argument that it's faster to prototype on Python is true for these kind of embedded devices. So maybe some of you agree with me, disagree with me. Please come and have a discussion afterwards. I would love to hear some arguments why this is eventually wrong. Okay, but once we got this device going, we can connect to it and we can get data out from the accelerometer. And that is the sensor that measures the movement of the juggling ball. And typically it looks like this when it's being juggled. So there is resting, and then eventually we throw it, and then we throw it, we apply a force to the accelerometer that we can see here, and in the second we drop the ball because it leaves our hand on the way up. Instantly the acceleration drops to 0, and it's actually 0g because the ball is accelerating downwards as gravity is also pulling it downwards, so that comes across as 0g and not 1g that some of you might expect. And then it's going to be airborne for a little while, and then it's going to land in your hand, and depending on how soft you are able to catch, if you are kind of really able to do like this, you won't get these hard spikes. That's because at least when I juggle, I tend to almost sometimes meet the ball a little bit and I kind of catch it like this. And that's why we get this one sample of a really, really high force acting on the ball 15G in the moment it lands into the hole. And of course, the challenge for us is that we want to have juggling balls that are smart. So we want to convert this data into a Siteswap number. Is it a 3-throw? Is it a 4-throw? Is it a 5-throw? And so on. And the students in this project went onto this in a very, very kind of mathematical approach. So they took the equations, the juggling equation that I mentioned to you initially by Claude Shannon, and they tried to make a little equation that expresses which Siteswap number do we get from throw. So here there's a lot of stuff, and especially it's this line here in the middle that says that the throw unrounded is twice the velocity, there's a gravity, and there's some constants, and the dwell time and the beat time. The dwell time is how long you hold the juggling ball in your hand before you throw it again. It lands, you hold it a little bit, and you throw it. That's the dwell time. And the beat time is the entire time before a ball is being thrown again, the frequency of the whole pattern. And the problem with this approach, this kind of, in one way, I think this is novel work done by the students I supervised. They have really done a good job of combining Siteswap and available physics and so on. But eventually this fails. And the reason it fails is that if I juggle 3 balls, and you see that there's an estimate of the velocity based on the accelerometer, how fast the ball is leaving my hand. But the juggling pattern can look quite different because I can juggle very, very narrow. And then the ball goes straight up against gravity. And as I extend my hand faster and faster, the tempo actually increases, and I can't talk anymore. And I throw really, really hard. The acceleration of the ball becomes higher. So the exit velocity is higher, but it's still a Siteswap number 3. So when we try to do this and apply it into coloring of these different throws in different colors based on the juggling, it actually fails, doesn't work that well. So we need to hard code an equation like this into the code. In the moment it involves humans and so on, it's actually not a good idea. You will need something which is much more flexible and kind of adapting to the behavior of the human. I think that's one important lesson from this project. Yes, it can be compiled for faster execution, but still in these juggling balls that are running on 96 megahertz, we are still able to get only about 60 or 70 hertz sample frequency on the accelerometer, how fast we measure. Whereas on an Arduino version that I worked with many years ago, which had a much cheaper and much slower microcontroller, but the program written in C, then I could easily achieve 200, 250, 300 hertz sample rate. So that's also partly why this project didn't work out. And it's also particularly due to the one throw, which is like this, right? How long is the ball airborne? Especially if I'm a little bit narrow, you won't actually be able to detect the free fall because the sample frequency is too low. So therefore, we have a little bit of further work. We could imagine that we do a little bit of increasing the sample rate, do some kind of code optimization to see if we could make it go fast enough to increase our sample rate. And I think it would be very interesting to have some kind of adaptive algorithm for throw identification, so that when we are throwing something up and we get a velocity, when this ball eventually lands, if they have radio communication and they talk about when they are being thrown and when they are being landed, the ball will, based on this radio communication, know whether it was a 3 or a 4 or a 5 with absolute certainty when the other balls are being thrown. And therefore, we could use some kind of machine learning or some kind of adaptive algorithm that converts acceleration or velocity into a throw based on this. So that would definitely be a further work which I would love to do if I can find the time for it. Okay, I see that there's a few minutes left. And unless you guys are completely full, I think I will spend a few minutes just trying to put this into a kind of historical context. Here's just when we had the first test of the juggling balls. These are two of the students who programmed everything, and they are looking at me with this kind of fear. Oh my God, is it going to work? We had a very good time at Høgskolen Krona to have this testing. And when it works, we are all a little bit more relaxed. So let me start by asking you guys a question. Initially, I set up a few axioms, this kind of absolutely certain truths, and then we use logic to deduce the logical consequences of these axiomatic statements. How old do you think this way of reasoning is? Who was the first one to reason in this way and write it down into a book? Any ideas? Anyone want to try? Probably the Greeks. That's a very good. Do you have any particular Greek in mind, or just the Greeks in general? Plato. Good try. Huh? Pythagoras, yes, maybe. I don't know if he wrote it down, though. The first guy to do this very, very systematically was Euclid. And Euclid wrote a book called Mathematical Elements, in which he made 10 or 15 axioms and assumptions, and then he deduced everything in two-dimensional geometry that we know today, squares and triangles and all these kind of things. And here is a copy of one of these documents. This is an old copy from approximately year 300, and this is in the possession of the Vatican, and it's referred to as Codex Vaticanus. It's one of the oldest copies of Euclid's Elements. And here you can see the famous a squared equals b squared plus c squared derivation in this book. Another community which has spent a lot of time to try to make axioms and then deduce the logical consequence are the people who deal with origami. So origami, of course, being the art of folding paper in certain patterns. And this is one of the traditional Japanese patterns, the crane. And of course, people start after a while, when they discover that this could be mathemized and formalized, to fold much, much more complex shapes. And here is a horse. And if you don't think this is sufficiently complicated, people do things like this. And remember that they do this from one single sheet of paper with no cuts. So it's only folding to get into these kind of patterns. And there's a really beautiful, which is this little friend, a mantis, a praying mantis, I think they are called. And here we have some kind of insect. And this, by the way, is the crease pattern, which tells you which way to fold the paper. So the red lines folds one way, the black lines fold another way, and the circles becomes these different things that prolongs and protrudes out from the body of these things. And the reason that this was possible is somebody managed to axiomate and formalize the entire field of paper folding and origami. And now I can go back to the stuff that someone was laughing a little bit when I said, I want to make a smart juggling ball and understand how it's being juggled. Because on the face of it, it seems like a completely useless thing to do. Why would you do that? What's the point? But I think the lesson learned, especially from origami, is that when you really, really know how to fold things based on mathematics, then certainly you can apply this to new things. Because at some point in history, we decided that it was convenient to have satellite TV, or we want to have satellite communication. So we need to send these satellites into space. And they need power somehow. So they have solar panels. And the thing is that the solar panels are super big surfaces, but you want to put them into a square box. So how do you fold that solar panel to make it into something that you can put into a box? And of course, when NASA started doing this, at some point they met some of the origami kind of paper folder people, and the paper folder people said, hey, this is easy, we've done this for a long time, problem solved, just come to us and pay us, and we are going to do this for you. So there are these really, really beautiful shapes that people make. So here is just one such example. So when it's unfolded or in its packed state, it looks like this. And then you can pull in these kind of things, and then eventually it folds flat. And once you have proven it on ground, then you can build a solar panel for real, and you can send a panel into deep space, and you know exactly how to fold it out to get the energy. That's all I had. Thank you very much.